So video you can on it actually.
Okay, that means. My video is on. Hey, can you see me? Sunny?
No, actually.
No, it was
Yeah.
actually the Mac is giving an error that your camera isn't sending any video. So
I think we can start because time is running out. So
yeah.
uh, you can share the PPT and yeah.
I think I have shared. Yeah, you see, this is a full screen.
Yeah, okay, okay. So I will introduce. Yeah, good afternoon, all of you. Welcome to today's talk, and today's talk is given by Dr. Mohan TS, and he's scientist in NCMRWF under Ministry of Earth Sciences, and he has PhD from the reputed Institute National Atmospheric Research Laboratory, and he had extensive postdoc experiences, and he has many papers in research related to convection and atmospheric dynamics and the related areas. So he has many publications in the area, and so I request Dr. Mohan to deliver the talk. Thank you.
Thank you, Dr. Unikrishnan. I am really privileged, and thanks for giving me this opportunity to share some of my recent. I'm not actually going into the results, but then um, this is yeah, dynamics. I want to talk about the thermodynamics only because when I was doing my postdoc IPRC, we were working on the monsoon mission project, and at that time we were working on the moist convection. So from that time onwards, I am till now even at NCMRWF. Majority of my work are based on the moist convection, convective process, and studying the convective process in a global model. This is the line of work that I am doing from past 7 8 years. So I can say that I will mostly concentrate on atmospheric instability and convection kind of a thing. Although the title was saying that the dynamic meteorology too, I'm afraid that I may not be covering dynamics right now. But if you have any questions, I am ready to clarify during my presentation. And with that, I will start my talk. And today, the title of my talk is the understanding atmospheric instability and convection. I don't know the audience, Dr. Unni. These are audience are all students or any. Can you just? I haven't seen the audience. So yeah.
They are PhD students from NCESS and other institutions.
Other institutions. Okay, thank you. So this is basically I am just touching the fundamentals. You can say that my talk would be two parts. Um, in the first part or the first half an hour or maybe 20 minutes, you can see all the basics that I'm covering, and then I'll go a little deeper into moist convective process. What are the moist convection? How the moist convection can be represented in especially in tropics, and what are the challenges that we face during the moist convection, and how do the models tackle those things, and what kind of tools that we use to understand the moist convection. That's what I will break my talk into two parts. So with that, so like he already gave a nice introduction, so I just want to say that I'm my main core was the subseasonal variability and predictability during monsoon, and then process oriented diagnostics is right now what I am doing. So the basic agenda of our talk is I will touch upon the fundamentals, some of the thermodynamic aspects of the convection, and basic thermodynamics, and thermodynamic diagrams, stability indices. You might have come across all these things, but just to recall your guys, and then also me, just want to see how these can be used in our daily research and daily understanding the weather phenomena that is happening on tropical regions. Just touch upon these things and how the observations and models, what kind of observations and models we use to identify these indices or the phenomena. And then finally, I end my talk with the moist convection and what is the main tool, that is the moist static energy, how we get that tool. That's the agenda. And by the end of the talk, probably you may you may feel that you may had a chance to learn all these things aspects. So with that, when I say start the fundamentals of atmospheric instability, um, what exactly I mean by instability? Everyone knows that this is the instability process that is driving the atmospheric circulation, and then it only gives the rainfall, because atmospheric instability and stability parameters both drives the atmospheric and environment. So before going into the stability aspects of the atmosphere, we need to know some of the basic concepts, that is the um, pertaining to the atmospheric instability. So in that line, some of the one of the basic thing is that the temperature changes, because if you know the environment in the daily life, if you see, everyone knows that the environment temperature goes and decreases with respect to height, um, and then the pressure decreases with respect to height and until troposphere. Then again, the temperature profile, if you see, it has its own inversion, and then sometimes it goes to increases the and different layers. So I'm not going into above the above stratosphere or above the tropopause. So if you consider atmosphere, most of the convection and which was affected by human life and the daily life, we confined ourselves to the troposphere. So in the troposphere, the temperature changes is and the moisture change is very much important. And being residents of tropical atmosphere and then tropical latitudes between 32 plus 32 minus 30 degrees on either side of the equator, we are very much affected by the moisture changes, because this is the only region where we have an abundant amount of moisture available. This is where the moisture envelope region, and the main the variable that we need to look is that the moisture and temperature in the tropical region. So if we know that the temperature changes and the moisture changes are the main culprits or the main drivers for the atmospheric instability. So this, we need to know about what are these things. So if you look at the temperature changes, fundamental thing is that the adiabatic temperature changes in the atmosphere. I think you know the adiabatic things. If you look at the first law of thermodynamics, you can see the adiabatic process is where you don't expect anything, any exchange between the amount of parcel that you are taking or a flux that you are using to study the environment, and that one doesn't had any interaction with the surroundings. This is the adiabatic process. So no, so this is a basic assumption in the meteorology, and you come across in any textbook or any thermodynamic textbook. This is the fundamental assumption in the textbooks. They made that the atmosphere or the parcel that we are working on the vertically, temperature changes or moisture changes that we study, we assume that the parcel is adiabatic, but means it doesn't do any exchanges with the atmosphere or surrounding environment, which makes our life little simpler, because if you consider that the adiabatic changes is not there and the parcel is exchanging heat while it is moving up and down in the atmosphere, we have to add some complexities, and then that will make the understanding the phenomena a little more complex. So to reduce the complexity, we assume that these adiabatic changes. So when you consider the atmosphere is adiabatically, it doesn't have heat exchange anything. So like I said, atmosphere we go on decreasing the temperature with respect to height. So if you consider it is a adiabatic, then it is adiabatic lapse rate. Adiabatic lapse rate can be F2. If you don't consider moisture at all, like adiabatic lapse rate during the sunny weather, like sunny, no convection, no clouds, nothing, incoming solar radiation is coming, everything is onto the surface and everything is going the long wave cooling, they are balanced. Then in that case, the lapse rate would be the dry adiabatic lapse rate, because there is no moisture involved in that. The lapse rate that is happening is the adiabatic lapse rate. And in between, if you had any questions, please ask me, stop me, and then I will clarify. So this is the dry adiabatic lapse rate that I'm talking when you don't consider any moisture inside your parcel. But when you ingest moisture into your lap state problem or the lap state things in the vertical temperature lines, then you will come up with a moist adiabatic lap state. So those lap states will be different. Now you know that the atmosphere is a combination of different types of gases, starting from water vapor to everything is there. But for our purpose, the water vapor is the main source that we study. So without moisture in your column, in an atmospheric column starting from surface to the troposphere, from 16 kilometer, in that entire column, if you don't consider moisture at all, the temperature decreases along the adiabatic lapse rate values. And then when you ingest the moisture, the rate of decrease will be slightly lower because you are ingesting moisture in it, but the moisture has a different value of decreasing its temperature when you are adding something. So that moist adiabatic lapse rate would be slightly lower than dry adiabatic. So now you have a dry atmosphere and a moist atmosphere. So dry convection and a moist convection. So they have a two lapse rates. So the dry adiabatic lapse rate and the moist adiabatic lapse rate. Those two lapse rates are very critical. First of all, any atmospheric phenomena, if you want to understand, you need to understand how these lapse rates are changing, and these are very critical to understand the weather patterns. Now, like I said, atmosphere is a composition of different set of gases. You know the ideal gas law. It follows this. I think everyone knows this ideal gas law. This the pressure of any parcel that is going on, it's a multiplication or the sum of the dried gas constant and the temperature and along with the density. So that means the gas follows this law, that the decrease of the pressure with respect to height is a function of both density and temperature. So this holds good until the 100 kilometers of the atmosphere. When you consider this ideal gas law, the specific heats also, you have to see the specific heats, because when you raise the temperature, if you are either you are raising a temperature by 1 degree when you are increasing the temperature of the parcel, or when the parcel is decreasing its temperature by 1 degree. So either way, if a 1 degree change in the temperature, the amount of energy or the amount of heat that liberates, or the amount of heat that uses to convert energy from one form to other form, is your specific heat at constant pressure or specific heat at constant volume. These two are the other constant that we daily come across in our daily thermodynamic meteorological aspects. And the other aspect that we need is that the hydrostatic balance. Let us say that if you don't have any atmospheric motions, like there is no, you know that different forces acting on the atmosphere parcel. So one of the forces is the gravitational force. If you consider that there is no atmospheric motion, whatever the gravitational force that is acting on the atmosphere or the on the amount of air parcel would be vertically balanced by the pressure gradient force. This is a vertical pressure gradient force. You have the two pressure gradient force. One is the horizontal pressure gradient force that drives the momentum equations, and the other one is the vertical pressure gradient force, that is the restoring by the gravitational force. So when you consider these two are balanced, the vertical pressure gradient force and the gravitational force, and this is called the hydrostatic balance. And this is very important. Again, this is another assumption. Mind you that the first assumption I told you, that the atmosphere is the adiabatic process, and the other one is that the hydrostatic balance, and the other one is that the atmosphere always follows the ideal gas law. So based on that, you derive this. Your all these equation has come up in the NWP equation that we use daily. So these are the assumptions that they made, but these things holds good for majority of the cases. But there are some limitations, like here hydrostatic balance doesn't applicable when the phenomena having a large vertical accelerations, like tornadoes or very deep convective systems with updraft, very extensive updraft. So now when you say that it is failing some of the conditions, then how it can be used as universal? Then the question comes, then you can answer saying like this, that the atmosphere or the environment that's surrounding the earth is a fluid, which is a continuing fluid. But what happens is that these tornadoes or these deep convective systems are the perturbations. When your fluid is in continuing motion, these perturbations are very transient. That means the perturbation, or you can say the prime components in any, it's mean plus prime is your total component. So in the continuous fluid, if you consider the perturbation, their contribution towards the steady state, or towards maintaining the flow, is very minimal. So these things happens very minimal, right? The tornadoes or the extreme weather events, they happens in throughout the year. You can find out in numbers. So that means sometimes these equations or these balances fail only during this kind of an extreme weather event. So otherwise, majority of the motion that is happening on the tropical atmosphere follows this kind of a hydrostatic balance. That's why now the models for those kind of systems, models are now, earlier it was the hydrostatic balance models. Now the non-hydrostatic models also came up in NWP. Um, so now when I say that the parcel moving up and down in the atmosphere, that drives the that is what is the key factor in driving the stability of the atmosphere. Because to convection to happen, or to understand the thermodynamics in the column, like I said in the few slides before, the stability is important, because the parcel is moving up and down. Now when I say the stability in the atmosphere, parcel is moving up and down, what does that mean? Like, if you see the visualizing the parcel, like, as a circle, and when you look at this parcel, when this is the steady state, the first graph, that is when this is in the initial perturbation. Initial perturbation, when you give the initial perturbation of the parcel, when it goes and come back to its normal position, like in the second graph you see the stable, that is called stable. So as it is not going up, it is still, once the initial perturbation is over, the energy of the initial perturbation is over, it's come back to its normal position, that is the stable condition. But if it is continuously go on rising above the atmosphere with respect to height, then you can say it as a unstable. But even the initial perturbation doesn't make any changes into that parcel, that is called the neutral conditions. So it all depends upon how the parcel is moving and the amount of the perturbation that you are giving into the parcel. So here the keyword is your initial perturbation. Now when you have the initial perturbation and the parcel is doing its either this stable, unstable, or neutral kind of a trichotomy law, based on the parcel initial perturbation, then the immediate question comes into our mind is that, is there one instability, or do we have are we encountering very different kinds of instability? Because different seasons, different moisture conditions, different atmosphere, different weather phenomena, are we having the same instability or different instabilities? When you look at the types of instabilities in the atmosphere, um, it's like I said, the instability is because of the vertical air movement with respect to height, that drives the circulations, because that makes that induces the cloud formation, cloud development. So we have absolute instability. That means when it occurs when it is super unstable conditions, and it kind of like I said, it is kind of a continuous rising of the parcel. So it generates a deep convection, and associated with deep convection you will have a very strong upward motion. That is your absolute instability. The other one is the conditional instability. That means the conditional instability depends upon the moisture content, because the earlier I'm not saying about the moisture content, but conditional instability depends on just amount of moisture, whether the moisture is sufficient, or whether the moisture is changing its phase. um, it starts with the vapor and it became liquid, and does this has an effect on the instability or the stability of the column, then you have to use the conditional instability. And the other one is the potential instability, is the layered atmospheric condition. But potential instability is because when you have a slantwise convection, if you consider the parcel as a just a whole infinitesimally small thing that is going up and down with respect to the height, then you have this absolute or conditional instability. But if you consider the atmosphere as the layers or its slabs, then you have to use the another instability called the potential instability. That also needs in some kind of a scenarios. I'll come up this slantwise convection when in my down the line slides. But what I want to say is that there are different kinds of instabilities exist in the atmosphere, even though you have moisture and temperature, the two variables that you have, but based on the different scenarios and weather phenomena, you have to use the different instability conditions. Now the immediate question, why we need to study about the stability and what is its important? Like I said, it is the vertical motion that drives the circulations, and it is the one that is giving your precipitation, much needed quantity for everyone, the human life. The instability is important, vertical motion. it has a two movement. Again, what I'm saying is the parcel has either parcel goes up or parcel comes down. When the parcel is going up, it gives the deep convection. When this parcel coming down, it is a suppression. It is a kind of a drive. Um, this I will tell you what is when it is coming down. There's adiabatic expansion and adiabatic compression. So when it is parcel is going up, it is adiabatic expansion. The parcel doesn't exchange anything with the surroundings. So everything is happening inside the parcel. So because of that, it expands like a balloon. Where expanding air cools, low temperature physics, and then it changes its phase, and then it releases its convection, release latent heating in the parcel, and drives again. It's a positive kind of feedback. But how about when the parcel is coming down? What happens when the parcel is coming down means it is adiabatic compression. Again, the assumption is adiabatic. Nothing is going inside the parcel or coming out of the parcel. So even in that case, when the parcel is coming down, it is adiabatic compression. What happens in adiabatic compression? It's the warming. So adiabatic warming is a called your descent, which makes the atmospheric column warm. Total radiative heating will be warm here. Positive temperatures will be here and then enter the column, and that will kind of give a low level divergence, and so on and so forth. It leads to suppression of the convection. That's why when you see the deep convection time, you have a strong upward motion, and then the descent kind of a place, you will have a strong downward motion, because downward motion gives the suppression of it. Now when I say we have parcel is going up, parcel is going down, now the question has to ask that how the parcel is going up. Is it going on its own? Somebody is pushing it. So the question is that the answer is, when you have this kind of a scenario, the parcel can go on its own when you have a strong heating surfaces. That we in general daily life we see that in the pre-monsoon conditions, sometimes there is strong thunder showers in the afternoon, especially in West Bengal or that part of region called Baisakhi. So you have a moisture available and you have a strong heating in the pre-monsoon. You no need of any forcing. It gives its own local thermodynamics acts, and then you will have a strong parcel movement, and it can generate this thunderstorms within no time. Like within 2-3 hours, you will get a strong, very deep, intense thunderstorm, and then it can give a plenty of rainfall and devastation that it can do. That is one thing. The other one is the forced movement. The forced movement is that you have a parcel, but it doesn't have any like heating kind of a thing, but with the mean wind, or you have it is come acrossing terrain kind of a surface, or it has to lift on its own by some obstacle, like windward kind of a thing. Like, the west coast, it has strong orographic precipitation is one example of forced movement, because you have forced lifting of the parcel because of the mean wind. That can also give you the upward motion, that can give you the good intense convective event. So there are two. The other one is the buoyant movement. Buoyant movement is, like I said, it's on its own. When it is because of the less dense, as soon as the heating from the surface, it becomes less dense and it buoyant. So there are two movements. One is the forced and buoyant movement. When I say buoyant movement, forced movement, let's keep it aside. When I say the buoyant movement, buoyancy comes into the picture. The buoyancy is nothing but the parcel, the floating of the parcel. In general, if you see the meaning of the buoyancy, is it the floating, how the parcel float in the atmospheric column. Now the parcel rise in the atmosphere because its
Sir,
density
I
is
have a
less.
doubt.
Yep, yeah, go on.
Sir, the parcel is generating due to surface heating somewhere, and it is reaching near to the hill station, some like a terrain. So
Uh-huh.
it will be considered as force when.
Um, uh, there are two aspects here. When you consider a column, the heating is from the below, right? Heating is from the below. The parcel is going up. But if it is, the mean wind is horizontal. The mean wind cannot be vertical, right?
Yes, sir.
It is moving to hill station means the mean wind or the background winds are either horizontal, the easterlies or westerlies. Although your local thermodynamics is showing that the parcel is heated up and it is going up, it has to come across the mean winds. Now, actually, you are a good question. The thing is that your mean wind generates its own vorticity. Imagine like this. Um, in a hot plate, or in a stove, you are putting some water and you have started boiling the water, so you can see the bubbles, they are going up vertically, right? In a
Sir,
horizontally, if you are sending if you are giving some kind of a force winds to that vapor, what happens? It goes away from the stove. The steam goes away from the stove. What that
ye-
means is that the vorticity that is generated by the mean wind, if it is matches with the vertical relative vorticity of the parcel, then they both can go in the same direction. But if your vorticity is not matching or in phase with the vertical movement of the buoyancy, then you will have a suppression or kind of a thing. So it is a tussle or tug of war between the horizontal vorticity and the vertical, spin of the parcel. So in that case, if one is overcoming, the parcel can be considered as a force lifting. If vorticity is very strong, if the mean winds are strong, otherwise it is the simple thermodynamical aspect of the parcel that is going up.
And sir, another question. Yes, sir.
Yep.
One doubt, sir. Kal Vaisakhi, you mentioned it's a local thunderstorm. Can you a little bit can you explain about it?
Kal Vaisakhi is like during pre-monsoon condition. What happens is that, or the head bay of Bengal, you have a plenty. Normally, that region is considered as a moist region because you have plenty of water bodies nearby, and the mean winds are during that time it is easterlies or that part. Okay, around that Chandipur, Odisha, and West Bengal, that triangle, small triangle, that part is you have a mean easterlies, and lot of moisture is coming from the head bay of Bengal. Instead of that, you have a very strong incoming solar radiation, that's pre-monsoon solar radiation, that's already heated up your surface. So your
Yes,
surface is already gained enough energy, and your sensible heat has storage in the sensible heat in form of sensible heat during that part is enough. And you are now, with that sensible heat, you are adding some moisture to it. It is like hot plate, you just put some water vapor. What happens is immediately it evaporates, like. So
yes,
similarly,
sir.
you're just a heating surface with a abundant sensible heat from the pre-monsoon is giving a thermodynamic condition. It sets up the stage. Now I'm just ingesting some moisture. You want to see what happens to that moisture. It immediately lifts that moisture and generates convection within no time. And mean winds are happening, the steering winds are in such a way that the vorticity, like I said, the steering winds, the vorticity is helping the convection to grow. In general, what happens is that the shear or the mean winds can help a convection in three ways: either it suppress the convection, either it intensify the convection, either it neutralize, like that's required. But here in the Kal Vaisakhi says, since you had moisture and the mean winds, shear and everything happens in they are in place, so they are all together. It's a combined effect of all three that you are getting this kind of a thermodynamic deep convective system.
Thank you, sir.
Yep. So when I say the buoyancy of the air parcel, it is less dense from the environment, so it goes. So you can see here I gave that the parcel temperature, if it is greater than the environment, or the density of the parcel is less than the environment, in either way, vice versa, you will have the positive buoyancy. And similarly, if it is less than the environment temperature, or the parcel's density is more than the environment temperature, then it is a negative buoyancy. Parcel comes down. So this is one is if it is a negative buoyancy, you call it a stable condition. If it is a positive buoyant parcel, you call it as an unstable condition. Like I said, the lapse rates I already touched upon. This is dry adiabatic lapse rate. When you compute the adiabatic lapse, just want to show you that what is the dry adiabatic lapse rate. You know that temperature decreases with respect to height. That is the lapse rate. Lapse rate is nothing but your negative value of your temperature gradient. So dT by dz is your temperature gradient. And when you use that ideal gas law and then the first law of thermodynamics, and you do your math, and you can find out that the dry adiabatic lapse rate is nothing but your G by Cp. G your 9.8, and the Cp specific at constant pressure is 1004 joule per kg. So you end up with 9.8 Kelvin. So it is approximately 10. So dry adiabatic lapse rate, you normally people will take it as a 10 degree Kelvin per kilometer. So each kilometer 10 degrees in the temperature. If it is happens in your sounding, or if you see in the real atmosphere, then you can say that atmosphere is a dry adiabatic atmosphere. There is no moisture. Like this is schematically I'm explaining here the expansion of the parcel. If you see the figure, the rising parcel expands, and then the temperature decreases. This is, you can see the thermometer, the temperature decreases when the parcel is rising up, but when the parcel is sinking, adiabatic sinking will increases the parcel temperature, that it becomes the warm. This is how the parcel goes up and down along the temperature line. So now I said the dry adiabatic lapse rate is 10 degree Kelvin per kilometer. How about the moist adiabatic lapse rate? Moist adiabatic lapse rate, pardon, here degree symbol came. So this is actually Kelvin per kilometer. Okay. So the moisture adiabatic lapse rate, because if you include the moisture, how much it is decreasing? It is generally between 5 to 6 degrees centigrade Kelvin per kilometer. You consider as a moisture adiabatic lapse rate. Now the question is, what kind of a conditions in the atmosphere can stabilize or destabilize the this instability? I mean, like, whether they can enhance or whether they can suppress. So what kind of scenarios that we can come across this stability or instability? So one is that the radiative cooling of the surface at night. You can see this radiative cooling of surface at night in two cases. One is the desert regions, when you have so much of strong incoming solar radiation during daytime, but suddenly during night time, whatever the radiation that came in, it goes up because there is no clouds to abstract, to make it as a barrier and trap the radiation. So everything goes up. So it's a long wave cooling. Everything is losing. So it is a cooling. The other one is the advection of cold air near surface. Suppose the surface is there and then some cold air is coming, so that also can stabilize the atmosphere. These things are stabilize the atmosphere. Air moving on over a cold surface, like you see that a warm air or the cold surface can also make this kind of a stabilization. This is snow. So adiabatic warming due to compression, the sinking, this also can stabilize. When it is partially unstable, the partial goes up. When it is partially sinking, the substance is a stable condition. So these are the top four that I'm showing here: the radiative cooling, advection of cold air, or the air moving over the cold surface, or adiabatic compression. These are all are different factors or different phenomena where you can say that the stable conditions are persisting.
Out of these factors, which
Yeah.
one makes the more unstable parcel? Which one makes parcel more unstable?
See, among these things, the usually occurs thing is the radiative cooling of the surface, because the advection of the cold air moving on the cold surface is a special scenario, like in a fronts, or if you have a mean winds, strong mean winds. These things only can happen. Otherwise, the majority of the region, majority of the place, the radiative cooling is the one that is happens. In other words, I cannot quantify, but I can say vaguely that radiative cooling of the surface at night would be the more stable or destabilization condition. Among all the four, the top one is the major in terms of numbers. Radiative cooling could be the majority. So just schematically for you people, I just want to show you that now I told you two things. One is the stability and instability. What things can stabilize and what things can unstabilize, destabilize the atmosphere. So the picture here on two pictures, one is absolute instability and the other one is the absolute stability, like the title shows. Sources from the internet I had downloaded here just to give a pictorial representation of these things. Let us consider a parcel that is hearing at the 40 degrees centigrade, because the initial parcel is also in equilibrium with the environment. So environment is also 40 degrees centigrade. You can see here when it decreases with 10 degrees centigrade per kilometer. So in 1 kilometer, the parcel goes to 30. Okay, because it is going on a dry adiabatic, because this atmosphere completely is dry, the parcel loses its temperature by dry adiabatic lapse rate. So it is decreasing every 10 degrees centigrade, 10 degree along with respect to 1 kilometer, but the environmental lapse rate is slightly lower. Environmental lapse rate, let us say environmental lapse rate is slightly higher than this one. Okay, um, so 12 degrees centigrade. So what happens is that every kilometer you can see that parcel is warmer than the environment. This is what I'm saying. When the parcel is warmer than the T parcel is warmer than the environment, what happens is continuously rising, and then it gives you a strong convection. This condition is called the absolute instability. Now, when you forget about this figure and see these lines on the top, on the right panel on here, there are three color lines. One is the purple, blue, and red. The red is your until 2 kilometers, and then after that there is a blue. You can say that this is the red one is until the red one, that layer you can say is as a below cloud base or sub cloud layer or browned layer, whatever you say. There is no moisture here, or the moisture does not playing any role. The parcel is simply based on temperature, it is decreasing with respect to dry lapse rate. So it is red color. As soon as the moisture, once it becomes saturated here at the cloud base, now the parcel decreases with respect to the moisture, that is wet. So that is blue, wet adiabatic lapse rate. But the purple one here is simply purple one is simply here with the atmospheric environmental lapse rate. So again, this is absolute instability. Come to the absolute stability. What happens here? In the absolute stability, everything looks similar, but the only thing is that the environmental lapse rate is much less than the partial. That means the environment is cooling, and the partial is environmental cooling rate is much lower than the partial. So partial is much cooler than the environment. So that means the density of the partial is higher, so it will come down. So it doesn't give you any deep convective kind of thing. Some kinds of air clouds will form above boundary layer um, because still the partial is gets saturated, but not the deep convection. This is called absolute stability. There is lot of stability conditions happens in the boundary
Sir, I
layer.
have a doubt.
Yes, yes.
Sir, in absolute stability picture, so the environment, this dry adiabatic lapse rate is less than the environmental lapse rate. So why partial
no.
itself it is good?
No.
In second case, dry adiabatic lapse rate is less than environmental lapse rate. So that's why partial is not going. But sir, why it is starting to go upside? Like if its temperature, partial temperature is less than environmental temperature, so it should be sustained near to the Earth's surface. Why it is going up? Still, it is showing in picture. It is going upside, and then it is coming back.
Yeah, I can see here the temperature happening here. See, absolute stability means you don't completely regard in the atmosphere. You cannot completely delineate the moisture, right? Moisture will be there everywhere. Now also moisture is there. Whether if it is rains or doesn't rain, the moisture is still there, right? But the condition that is in the boundary layer is much stabler or is super stable than the when you have a moisture in it. Otherwise, the partial you cannot total air is your moisture and dry air, right? There's the combination of both moisture and dry. You cannot completely delineate the moisture from that. But when in that case, even in that case, if you have some kind of a lifting, you don't need any thermodynamics. If you have a lifting, then still you will get clouds, but they are not deep convective. In other words, you can say that some kind of a shallow cumulus or the layer clouds that is happening in the boundary layer, these are all because of this phase change of the parcel, but it is not because of the thermodynamic forcing. So there would be some kind of a cloud activity, but it is not deep convective. Absolute stability can be happen only in the boundary layer that suppresses the convection, but still you still have a moisture that can give you some kind of a clouds that is happening at some upper levels. That is, the congested clouds happens above 500 hectopascal. Nothing to do with the boundary layer. Even the boundary layer is stable or doesn't stable, it doesn't mind. The congested cloud that is happening in the 500 hectopascal, there the phase change happens, then you will have the moisture lapse. That's how he wants to represent that also. That's why he has given these clouds in the 500 hectopascal above 2 kilometers. Otherwise, in stable conditions, your boundary layer completely stable, no cloud formation happens.
Okay, thank you, sir.
Yeah. Now, when I introduced another concept called wet or moist adiabatic lapse rate, and then the value I have to show you that it is between 4 Kelvin per kilometer. So now, when you had, because of water vapor into that, that's what happens. Water vapor, if you introduce in your parcel, the complexities increases. Um, either in the lifting process, either in its phase change process, the moisture it is the main culprit in the tropical region, so it kind of changes it. So when the parcel is completely stable, that means your absolute if it is less than the environmental lapse rate, then it is called the parcel is completely stable. In terms of this is in terms of moisture, not in the dry adiabatic. When they both are equal, that is neutral. When the environmental lapse rate is much greater than the statutory adiabatic lapse rate, then you call it as unstable. So now the question is just to recall everything. How does the stability of the atmosphere can change during the day? What kind of things that stability can change? I told you, right? Just now I told you. So in the daytime, heating from the sun or boundary layer heated up from the below. Environmental lapse rate is steeper. That I already showed you that absolute stability can be instability can be happen when the environmental lapse rate is very steep, or otherwise in the morning and evening hours, radiation cooling, the boundary layer cooler. These things are different processes during morning, and I mean this is a diurnal variability of some atmospheric processes that also can happen, changes the stability condition. What I mean to say is that the stability is not it has its own oscillations. It can happen in diurnal scales, it happens in much smaller scales. So different processes during the course of the day, the stability on the lab states are changes, and they will change the stability of the atmosphere. To summarize, this is the stable layer, is shallow. The cloud types, you see, even if you have a stable layer, the stratus type clouds can form. It doesn't mean that the clouds cannot form. Stratus or altostratus, they form around some higher heights, but you can still feel that there are boundary layer from surface to where the boundary layer effects are there, the free troposphere, that stability will be there, but still there is a formation of clouds happens. That is the stratus kind of a clouds. When it is unstable, this is what answering your question, you can see that the stratus type of clouds can form during the stable layer also. That is also, I think, there's a lot of research is going on in the stratus clouds, and they are affecting the stability of the atmosphere. So different kind of a clouds, and different, you can see how they induce the cloud types in different conditions. This is just summary of those things. You can go on when I give the presentation to you, share the presentation. But now the another part of my talk is that you know that there is temperature, there are moisture, and they can give the stability. Those things can happen in the atmosphere, and they can induce the convection, and these things give you the different amounts of stability and rainfall, so on and so forth. Now, how do they represent? How do I know these things on theory, but is there any tool that I can represent in these things in diagrams? So from there it came to thermodynamic diagrams. I'm not going into the very details of the thermodynamic diagrams because I think a lot of time is already gone. So the only thing is that what I'm saying is that the key parameters of temperature, moisture, and pressure you represent in such a way that you can understand the environment by seeing some kind of a diagram. That is your thermodynamic diagram. So the initial first thermodynamic diagram that was invented was the pseudo-adiabatic chart, which is a potential temperature and temperature P and T. Only those two variables they have taken, because it all starts with the decreasing of temperature with respect to height, with respect to pressure scale. So the decreasing of temperature, the lapse rate with respect to P, they started doing it, and then they came up with the pseudo-adiabatic chart. Pseudo-adiabatic chart will be like this. On top right corner, you have see that figure. These are called adiabats, or the constant theta surfaces, or potential temperature surfaces, and this is your temperature, and your vertical scale is the pressure, logarithmic pressure. Now the main advantage of this thing is you can practically use this thing for adiabatic expansion or compression, because our main best assumption in the thermodynamics is that the parcel is adiabatic in nature. So if you want to see adiabatic expansion, whether it is going up or whether the parcel is going down in adiabatic compression, then you can, if you want to trace that parcel, this is the best chart to do that. So this is one advantage. But the disadvantage is that it can only happens everything in a small region of chart. You don't know what is, if you ingest the moisture, this chart is nothing of no use, because you cannot say anything, because it's a dry adiabatic only. So to overcome these things, QT charts came, that is called as QT. The T in the x-axis, here the T in the x-axis is straight, but in this QT, the T would be lightly skewed, and the pressure would be anyway logarithmic scale. So this is a QT diagram. I'm not going into detail. What does that mean? What does that QT looks like? QT looks like this. So it has different colors of lines. I think you guys might have seen this QT chart. Nowadays Python has all these codes to generate this kind of charts, and everyone drawing the soundings very well in Python code. But just to give a glimpse, this is your QT log P chart, where your isobars are horizontal lines. The horizontal lines that you see on the y-axis, your isobars, isotherms are skewed. They are slanted. Maroon color slanted is your isobars, and then saturated adiabats is your curved lines, and saturated mixing ratio is your dashed lines. This is your QT. Now there is one more diagram called T5 gram. This is the morning I am preparing this. I'm asking my student to prepare this, and she has done this. So this is T5 gram. Somehow we got this chart from the IMD. Thanks to Dr. Rajivan, he has given this chart. So with that chart, we had some data yesterday. We downloaded some data. Just want to show you guys how we can do that. So we could able to plot this T5 gram, and we can see that, again, here the T5 gram is your Again, your adiabats are nothing but your potential constant potential temperatures on the right y-axis, and your temperatures on the x-axis, temperature and theta. And your moisture or the pressure surfaces are inclined here. You know the three diagrams, the difference is one is the pressure and T both are straight, only theta is inclined. The second QT is T is inclined, pressure and theta are straight. Here the T and is constant, theta surfaces are straight, but the isobars are the isobars are inclined. So this is the T5 gram. So T5 gram, what you can do with this diagram? The immediate question is, what you have this diagram and you have these profiles, what you will do? Earlier days, they used to do this analysis to find out the nowcasting, whether to see whether the positive area between these curves, if I, they used to draw these diagrams and find out the different atmospheric conditions. For example, here I have used the pressure, temperature, and dew point temperature. Dew point temperature is nothing but your moisture variable. So any moisture variable you have to take. Like I said in the earlier, the temperature and the moisture is the main ingredients in the tropical atmosphere. So take the temperature and dew point temperature. You put the dew point temperature and T and dew point temperature and air temperature in the graph. The blue and red lines are nothing but your ambient air temperature and dew point temperature. Dew point temperature always on the left side of the curve because it is always lower than the air temperature. And you compute the cloud based level, okay, LCL. And then when you compute the LCL, I'm not going into detail, but if you compute the LCL and go on with the moisture adiabat line, these curved lines are the moisture adiabat. The area that is intersecting between the partial, the moisture adiabat and the ambient air temperature is nothing but your cape. This is how they used to find out the cape, and this is one time, and go to the next time sounding and see whether the cape area is increasing and sin is decreasing. So this is the condition instability. When your negative inhibition energy is very low compared to the positive area, then it is a chance to get a deep convective event. When a Kp is high means you will get a deep convective event. So they used to see the aspect ratio of the area and between these two curves, and then based on that they used to give a nowcasting of any thunderstorm or any event based on the T5 gram analysis in earlier IMD department. Now there is a software, so they will do that. Now when I say this, everything is now ready. The parcel is going up, parcel is going down, and you have the thermodynamic diagrams. What is this parcel? Nobody has questioned this thing. What is this parcel? Whether the parcel is a big blob or it is infinitesimal parcel, what is its assumption? That I already told you that 8 parcel it is moving up and down, and it can give you different conditions of the atmosphere based on its movement, and it goes on. The assumption is that it is always in hydrostatic balance with respect to the environment, and it is dry adiabatical when it is until the cloud base, and after that it would be moist adiabatic. So when it has these kind of qualities, that is a small unit parcel is called a parcel. So based on that, this is a simple parcel theory. Now, like I told you that based on this simple parcel theory, is first order tool to identify different instability and convection using this in the T5 grams. And there in the T5 grams, what you can do, you can identify different indices like LCL, your lifting condition level, where your parcel first becomes saturated, that is your cloud base, and after becoming saturated, whenever it is going up, that is your level of free convection. And again, once the parcel goes up and go at some time it loses its energy, and then it has to become equilibrium with the environment. That is your equilibrium level. The area between the equilibrium level and the LCL or LFC, your cape, and the area below the LCL and the surface is your inhibition energy. Again, when you have a strong inhibition energy, you need some lifting mechanism. Thermodynamics, if thermodynamics is not there, a lot of stability conditions are there, then you need some forcing mechanism to overcome this sin. So the other advanced theory is the slice theory. Slice theory is, or you can call it as a slice model of convection, where atmosphere is three-dimensional. To make our life little easy, what they did, they sliced the atmosphere in a 2D cross section. Slice in the 2D in the XZ plane. That means normally the slicing can be done along with the mean wind, aligned the mean wind direction. So let us suppose the mean wind is westerlies, so you have to slice along the latitude. So XZ plane, you take everything all the momentum equations or the primitive equations changes in that plane, and that means what is doing is that you are simplifying y term, like you don't need y term in the xyz equation. So you are you are somehow you are minimizing the complexity by taking a slice. That kind of that also some kind of scenarios slice method also useful, to identify the disconnected instability of second kind or squall lengths, to studying the frontogenesis of battle instability. This slice method is useful because slice method is considered the atmosphere or the it doesn't consider column, because it is a slice extended plane. It considers slabs or some kind of a blocks. So the block, when you consider the entire block, it can move all together at once, or one side of the block moves faster the other side of the block. You imagine that there is a strong rectangular uh, you know block, and one right side of the block is moving stronger and left side is moving, it is coming down, right? So this is a parcel in terms of slice convection. It is not a circle ball that goes up and goes down. Here the movement is two-way. One side goes faster, the other side goes slower. So in that case, you have this slice theory that is useful. So normally frontogenesis this theory is useful.
Sir, I have a doubt.
Yes,
Can I
yes,
ask
yes.
you? So you
On slice
told
theory.
if mean wind will be westerly, then you told we can slice like 2D XZ. We will slice. So how we will slice vertically or horizontally? Like my question is that.
It is you have x component and y component. You have two components. Now you don't have because let us say your mean winds are um, westerlies. Like I said, westerlies means it comes from west to east, right? So your x is your only zonal. You don't
Okay,
see
sir.
the
Okay,
meridional.
okay. Yes.
You understand?
Yes, sir. Now,
Only
yes, sir. Because X you consider a zonal direction means. Okay, sir.
yeah,
Okay.
zonal and
Meridional Y.
vertical.
Vertical. Yes, sir.
Yeah,
Understood,
zonal
sir.
and vertical.
Thank you.
If the
Thank
mean wind is your meridional, then you have YZ plane. In either way, what you are doing is that you are simplifying the three terms into two,
you. Yes, sir.
reducing
Yes.
circumference.
Okay.
The other one is
Yes.
the so now since you have all the theories, all the equation charts and everything, you understand the instability by based on lapse rates and everything. How do you quantify the things? So to quantifying the atmosphere or to quantify the instability, you know that instability is happening, but how much instability is really happening? Whether this amount is sufficient to have the deep convection. To quantify this instability things, you need the stability indices. Indices are nothing but your empirical relations, and they form by identifying different main processes that modulate the convection. Based on it, we have different kind of empirical relations exist in the atmosphere. Like I think you might have read in literature, K index, lifted index, total capes. In this, I am just mentioning few. Just want to show you that these are all empirical relations that will quantify the amount of instability in the atmosphere. There are advanced indices also exist nowadays, so I'm not going into it. But all these indices are useful only to quantify the convection. So this is a brief table of what you are seeing, the indices that I have given. These are those indices. Each one has its own advantage and each one has its own disadvantage. Some of the indices are single level, where it doesn't go beyond the other levels and doesn't know what is happening in different levels. The other let us say cape is an integrated product, doesn't give you what is happening in between. It just gives you the accumulated amount energy that the parcel possesses toward the column. Sin is also one other thing is that. So these evolutionary indices started with the single level and then goes right now there are different indices are there, where compared to cape and li, there are different indices which are much better than indices also came into the picture. So it is a continuous evolution to understand the atmosphere to quantify. The immediate question comes: why do you want to quantify? What you will do with the quantify? Since our aim is to predict the atmosphere, since our aim to understand the atmosphere and the prediction purpose, forecasting the atmosphere. So if you want to validate your model, you should have a benchmark of quantification so that you can validate your model, saying that yes, this is the quantification value happens for a particular region, like somehow deep convection or southeastern part of Kerala. Of course, you have a model forecaster giving some amount, but your observations, you already have observation which is giving some amount. You can have validation and saying that yes, the observations or the indices are saying that this is the quantification, but model is failing in that. Then you go on back saying that why the model is failing, so on and so forth. So these are the indices. So I'll skip this one because how do we measure those different parameters in the atmosphere based on different techniques? One is weather balloons, radiosondes, the other one is satellite, radar observations. If you all these things, you use all these things, ingest this information into the meteorological models and give the forecasting. This one. Now this I'll quickly. I don't know how much time I have, Uni. Hello.
So you can continue. We have.
Okay. Yeah. What I'm saying is that this is another important aspect is the moist convection and the moisture energy. Until now, this is very basics that atmosphere possesses instability when you have the moisture. Now you have the moisture convection and the moist static energy. What is this? When you include the moisture, the atmosphere, or when you include the moisture, the convection that is happening is the moist convection. And moist convection normally happens in the tropical regions. This is the basic difference between, I'm just showing the basic difference between the tropics and extratropics. You see this figure. This is a zonal distribution of latent heating. Okay, so if you look at this zonal distribution of latent heating, most of the latent heating is concentrated on anyone says that it is between 20 degrees south to 20 degrees north, isn't it? So the other regions, in other regions of the globe, the latent heating is very low. That means the tropical region, the main heat source is your latent heating in the free tropospheric atmosphere. And the other part, other phenomena, other things that is different from tropics and extratropics is that your temperature gradients in the tropical regions are very weak because incoming solar radiation completely concentrated only between 20 degrees south to 20 degrees north. It doesn't goes beyond that. So your gradients are very weak. And your large latent heating is there. Like I said, the vertical distribution of latent heating, you see very large latent heating, and the Coriolis force is very low. But if you go to the extratropical regions, you have a strong temperature gradients because solar radiation is not uniform at that place. That gradients will be strong, horizontal temperature gradients, and your Coriolis force is very strong, and your latent heating is very weak relative to the tropical atmosphere. This is the basic difference between tropical and extratropical regions. This has a profound effect on the deep convection that is happening in the different regions. The tropical atmosphere is complex because of this thing, whereas because the same thing, the extratropical regions are slightly easy to predict, and they have their tools to easy to predict the large scale systems and the cumulative scale convection. But we don't have any such kind of a stronger tool like quasi-geostrophic theory or quasi-geostrophic framework to understand the atmospheric motions in the tropical region. So the issue is we don't have, first of all, we don't need to understand the convection processes. Latent heating is not a it modulates the clouds, that is fine. Once the cloud forms, once the latent heating is a liberation of energy, right? It releases the partial releases the energy, but then again that energy uses to form the clouds. Now the question is like a chicken egg problem. Who came first? Is that the latent heating from the cloud that is forming drives the circulation, or it is the it is the cloud that is giving the latent heating? Kind of a question came. So to understand this issue, people has different theories exist. I'm not going into the latent heating concept here, but there are two schools. One is the convective instability of second kind. That school saying that atmosphere should be instability condition to generate a deep convection. It makes sense, right? The school one, whatever they say, it makes sense because you should have instability, conditional instability, then you will get a deep convection. That's what I told you earlier. That's what I showed you in the T diagram as well. But the other school says that no need to have instability in the atmosphere on the low levels. Still, you can have a deep convection because it is an adjustment process. It's a transient process, and it can adjust. What
Sir,
happens?
Can you show last slide for a while?
The previous slide.
Just okay.
Yeah.
Okay, sir. Thank you. Just.
What I want to say is here the two schools. One is the CISC mechanism defined by Charney and Elias in 1964, saying that you should have a low-level control of the convection to get a very strong deep convective activity. But the other theory, Narakawa school, but 1974, they came up with things saying that no, this is not at all needed. With just convection is an adjustment process. It just happens because in the continuous, as soon as it happens, it adjusts the atmosphere in such a way that quickly becomes equilibrium. But here they're saying that it reinforces the convection. In both the cases, what happens in the CISC, if you see this kind of a T5 diagram, this is this QT again. This QT diagram should be there to have a strong conditional instability. That means your surface should be very strong, low inhibition energy, and you should have a strong positive energy. When you have this kind of a sounding, you can say that this is conditional instability, and you can get a good amount of convection. But not all places over the earth, on an entire globe, an entire tropical region, these conditional instability soundings are very rare. Every time this condition doesn't satisfy. So this theory doesn't hold good in understanding the atmospheric convection. So then Professor Emmanuel and Thomas Kuppert, they come up with a theory called quasi-equilibrium adjustment process. What did they adjust is that atmosphere has its own, even if it is a deep convection happens, it's kind of, it doesn't reinforce the circulation, it just adjusts the temperature profile and becomes to normal. Like you can see, suppose let us say now you had a very strong deep convective event happening here today, so much of rainfall happened, but in 1 or 2 days the adjustment happens and the equilibrium happens and the atmosphere becomes normal. Yes or no? So this is the adjustment process. The adjustment scale is faster and the adjustment scale is slower, depends upon the convective, depends upon the intensity of the convection. Here the moist convection, when the dry convection, it is adjustment between the heat flux from the surface and the radiative cooling. The radiative cooling controls the upper troposphere temperature profiles, and the heat fluxes controls the surface temperature. These two are in tandem, and they can adjust the temperature profile in the dry convection. Dry convection also happens in the desert regions with just the dry convection. But when you ingest the moisture is a culprit, and it can maintain so many things. Again, radiative cooling will be there in the top of the atmosphere, because above the 15 or 14 kilometers, the convection suppresses. There, the radiative cooling again exacts. It's the top of the temperature profile is controlled by the radiative cooling process, but the lower it follows the moisture adiabatic. That's what I showed you earlier. The T5 gram or QT, any diagram, if you see, the moist adiabats are the curved lines. So the temperature adjustment would be like this. The temperature profile, if you construct in the moist adiabat or moist convection, it will not be straight line like this. It will be like a curved one. So this is the CQ. This is the adjustment happens in such a way that you give some perturbation in the boundary layer in the second figure, if you see. Similarly, the upper troposphere temperature also shifts, and both the things maintains equilibrium at some point. So that means the boundary layer and the upper troposphere both are in tandem based upon the initial perturbation that you give, and then they adjust together. This is your CQ adjustment. So now, to understand this CQ adjustment, what is the best tool that you can use? The best tool is nothing but your moistatic energy. So this is your moistatic energy. The tool that we are using is moistatic energy, and then how do you derive this moistatic energy? I'm not going into the details of the derivation of the thermodynamic energy. It is very easy. I will leave the PPT here, or I'll share the PPT with the thing. You can find out how it is. This starts from the thermodynamic energy equation, first law of thermodynamics, and you, in the first law of thermodynamics, you assume that it is ideal gas equation and the amount of heat supply, internal energy, these three, and you, instead of this nomenclature, you put these values, and and you change the rate of temperature profile, find out the rate of change of temperature profile, and then you end up with one heat source called J, that is adiabatic heat source. And then if you have a adiabatic heat source, then that heat source is nothing but from the radiation or the latent heat from the cloud or thermal conductivity, whatever it is, the frictional heating. So these things, if you put this in the first law of thermodynamics, you end up with two quantities called these things. One is the Cp, T, Gz, and Lq, that is called moistatic energy when you consider the moisture atmosphere. The other one is Cpt plus Gz is your dry static energy. Again, if you see carefully, Cpt by Gz, if you these two, if you see closely, this is nothing but T by Z is G by Cp, right? If you take this equation is equal to 0 on either side of the equation, then you end up with the lapse rate is nothing but your dry adiabatic. So this dry adiabatic lapse rate comes from this equation only. The moist adiabatic lapse rate comes from this equation. So these two are your moist static energy and dry static energy. Combining all these things, you end up with a because everything changes, whatever the rate of change of moist static energy, whatever the rate of change of dry static energy is nothing but your J, that is rate of change of heat source. The heat sources are the changes. When you put everything into this thing, you end up with an equation called moist static energy equation, that is this one. The rate of change of moist static energy is a combination of different terms. One is the horizontal, the vertical, and residual, and the adiabatic forcing terms. This is simple, like a primitive equation, like thermodynamic energy equation. You have a lot of literature available in the textbooks as well, then you can derive. Interesting candidates can derive this thing. And this is one of the best tool or a powerful tool in the topic to understand the moist convection. This is that tool. With that, I will stop here, and then I'm ready for any questions. Thank you.
The floor is open for questions. So if anyone has questions, please.
So I think potential instability more.
Yes. Pardon, ma'am.
Potential instability. Can you explain more about it?
Potential instability. I just briefly touch upon this. Potential instability comes with the slice theory, basically. What I said was here. Potential instability involves layer atmospheric condition. This is a slice, like in general, when you consider parcel as a cube, that is what our imagination, either a ball, right? So with a small one unit of its volume, how it is going up and down. But the potential instability is a layer wise. It is not a single parcel. It is a layer, or you can say that it is a block, or it is a slab kind of a thing. Now when you have this one, let us say the slab, if it is isothermal slab, the temperature of the slab or everywhere is the same, or with the T, that is fine. But if it temperature changes in different way, like you assume in the real atmosphere, the slab, let us say the slab is extending 1 degree by 1 degree in the model grid, let us say. That means 100 kilometers by 100 kilometers, or kind of a thing. So in that entire grid, the temperature may or may not same. So if one side would be warmer, the other side would be different. So when it is kind of this kind of a discrepancy in the initial partial temperatures on the slab, when this slab is entirely, if you force it to lift up, whether it's thermodynamics or mean wind, whatever shear, anything, then it has its own lapse rates. The one side lapse rate would be different, the other side lapse rate would be different. So then in that kind of a layered condition, when this kind of a slice condition, then you will get the potential instability. So that is it's not simple, but you have a different scenarios now. In the same parcel itself has different scenarios. One side it will be warmer, the other side that is called as a potential instability. So normally you don't come across this thing in the tropical regions, because tropical regions majority of the condition instability or the CQE, what I'm saying, absolutely. The potential instability when the frontogenesis, or you have the large air mass of one temperature, or the warm air mass and cold air mass will collide, kind of a things, then this potential instability comes into picture. Mostly this is extratropical, or in a region between 30 and above, this kind of a potential instability can be seen in practical, in general.
Yeah, I think if there is no more questions, actually we will close the session now.
Yeah.
We thank actually Dr. Mohan for delivering the talk, and thank you.
Thank you all, and thank you. The session is over now.